Good morning, folks. How are you today? Welcome to the spring semester at RIT. This is MECE 306, Material Science Apps Lab. My name is Vinnie Gupta. I'm a professor in mechanical engineering. I've been at RIT for almost 40 years. I have taught this course or a variant of this course maybe 20 to 25 years. Since we are online this semester, the best way to contact me is by email. My email is skgeme@rit.edu. I'll be very happy to meet with you face to face using Zoom by appointment. So send me an email whenever you want to meet with me and we will set up an appointment. All the materials that I'm going to show you are on my courses. So you should have access to all these materials. I have 4 teaching assistants who are going to help me teach the labs. We have 10 sections of the lab. So section 1, Anthony Lord is your TA. His email is listed here. Next 3 sections listed have Gitesh. 3 sections we have Tyler, and another 3 sections we have Jessica. I asked each of them to set up an office hour during the lab section timing. So for example, let's say section 1 meets from 10 to 12 on Mondays. This is approximate, I've rounded it up. I have asked them to set up either 10 to 11 or 11 to 12 as their office hour. This way, if you need help, you can contact them and they would be able to help you during that office hour. So if you have any questions about instructional materials or quizzes, you can directly email me. But if you have questions about your lab report grade, email both your TA and me. However, if you just need questions about lab procedures or reports, you can contact your TA by email or during the office hours and seek those clarifications. Okay, here are the course exact objectives. I want you to become familiar with the equipment for characterizing materials. I want you to learn how to prepare metallographic specimens, examine the microstructure, and understand the effect of heat treatments. Another very important objective is to be able to create professional and concise lab reports using spreadsheet and word processing software. You are going to learn some new spreadsheet techniques, and you should be able to interpret experimental results and compare them to expected results. And I want you to become familiar with ASTM standards for materials testing. In the library, you will find electronic volumes of ASTM standards. So once I tell you which standard we are using, you should be able to go into the library and look that particular standard up. I would suggest, since these standards are quite expensive, you might want to download a PDF copy of that standard for your own records. After completing the course, you would be able to do some simple image measurements and analysis. Now, I want to mention to you, when I'm saying you would be becoming familiar with equipment, you might be thinking, how can we do this online? And what I'm going to do is I'm going to teach you how to use a image analysis software called Fiji, which then you can use as a electronic or virtual caliper. And that is how you are going to do measurements. So you would be able to do simple image measurements and analysis. You would be able to determine tensile properties of the materials. You would be able to determine hardness values from image of indents. You would be able to identify and quantify phases in steel, and you would be able to relate material properties and processing to the microstructure. So we're going to talk a little more about this later on as you learn the terminology of the course. Now, you must be registered for either 304 or 305, a companion lecture material science course. So whatever book they are using, that is all right with me. I believe they are using the book by Askeladd. I do want you to download a free software called Fiji. You can download it from this site here. It is available for almost all computer platforms. Please install it on the computer that you'll be using for this course. So here is our schedule. Our semester has 14 weeks. I have divided them into 7 2-week segments. In the first 6 segments, you will be doing a lab and submitting a report, taking an online quiz, and submitting a survey, a lab survey. In each 2-week segment, the first week I will give a demo, talk about the theory and principles of the lab. So for instance, after we have covered lab policies, this week's lab 1, I am going to show you how to use the Fiji image analysis software. We are going to do Brinell hardness testing on a given specimen. You are going to then repeat the similar operations on a different specimen, perform the image analysis on the Brinell hardness indents I will provide you. So in the second week of the 2-week segment, you will be submitting a report on Wednesdays. So you'll be submitting a report for Lab 1 on February 3rd by 11 p.m. The same week, on Friday, your online quiz and lab survey would become due. Again, 11 p.m. Friday. So we will maintain this kind of a schedule, so you will be effectively submitting something every 2 weeks. So our first lab segment focuses on image analysis and Brinell hardness. Second lab, we are going to focus on strengthening mechanisms. We will do some tensile testing. Third lab, we are going to focus on cold working, learn about Rockwell hardness. Fourth lab, we are going to learn about tempering of steels and impact testing. Fifth lab, we are going to look at annealed microstructures in steel. And in sixth lab, we are going to look at continuously cooled microstructures in steel. And then in seventh week, we are going to have just a demo. There is no lab report, but we will have a final online quiz. So this should give you a big picture of the course. I want to assure you that you are going to get a very good lab experience this semester. So this will give you the overall picture also of grading. So we have 6 labs. For each lab, we'll have an online quiz, 20 points. We'll have a lab report, 50 points, a lab survey, 10 points, and at the end of the semester, a final quiz, 100 points. So our total score would be out of 580 points. There are no extra credit assignments to make up for poor performance, so please do it right the first time. I do not use the plus minus grading system. In my experience, the plus minus grading system is not as good as the whole grade system for the aggregate student body. That means majority of you will profit from whole grades rather than plus minus grades. And I'll be using the following absolute scale for grading. It's fairly standard: A 90 and above, B 80 and above, so on and so forth. So let's see each of the elements. For the bi-weekly online quiz, you'll have 10 multiple choice questions. Each question would usually have 4 choices. You are allowed 2 attempts, but if you take both the attempts, I'm going to count the average of the 2 attempts. The quiz is due 11 p.m. of the due date. No late submissions. I'll post the answers the following day. Each lab quiz is worth 20 points. Final quiz, I'm going to take questions that will be same or similar to those from these 6 lab quizzes. I'll schedule it on April 30. We'll figure out a time and so on and so forth. 100 points for the final quiz. Then every 2 weeks, you'll have to submit a lab report. It's an individual lab report. Please do not cooperate with other students. You will be submitting one Word file and one Excel file to Dropbox in My Courses. It's due by 11 p.m. of the due date. Again, no late submissions, 50 points for each lab report. Here is our lab report structure. So in the Word document, you're going to have a cover page, 10 points. It'll have effectively information about yourself. It'll have a half-page abstract. And then next few pages would be itemized critical evaluations and summary conclusions. So that's what 20 points. So 30 points for the Word document that you will submit. And then 20 points would be for the spreadsheet and plots. Please have one plot per sheet. That means do not embed it. I'm going to provide you a lab report sample, and I'm going to provide you a lab report rubric, grading rubric for each lab assignment. So let's see material science in a big picture. Why is characterization important? Now in your course, you will find out that material science, basically there are 4 interrelated things, so as to say. So we have structure of the material, which is related to processing of the material. So if we process the material in a different way, it'll result in different structure. Of course, if we have different structure, it'll result in different properties and different performance. So obviously we need to characterize structure. We need to even characterize processing because it might go through several stages. We need to characterize properties and over longer term measure the performance, which again will be by characterization. So this material science lab is very, very important. You can see it plays a big role in all of these things. Now here is a very interesting thing. Imagine, for instance, you want to manufacture something. Let's say you want to manufacture a metal cup. So you start with a sheet metal and you're going to form it in the shape of a cup. So before you shape it into the form of a cup, you want that metal sheet to be very soft because you want to be able to shape it in a cup form. But once you form it in a cup, you want this cup to be very hard and very strong. In fact, it should be ideally non-deformable after you have shaped it in form of a cup. So from the same material, you are asking 2 things. Before processing, you want it to be very soft. After processing, you want it to be very hard. So you are demanding a lot out of the material scientist. So you see, just in giving you this big picture, I have used several words such as hardness, strength. I'm saying material should be strong, material should be hard. So I'm going to be using terminology that we will have to define very, very carefully. Not only that, I'll be using words that you may understand more completely as the semester goes along from your lecture course. but I hope to provide you at least definitions or things we are going to be using. So another thing you will come across in beginning of your course, hopefully, would be the type of bonds. So you know that we have three limited type of bonds. We have metallic bonds. So principally metals have predominantly metallic bonds. We have ceramics, which are predominantly ionically bonded. We have polymers, which are covalently bonded predominantly. And then, of course, there might be secondary bonds between molecules. We are going to focus mostly on metallic materials in this course. So we will be interested in metals and alloys, and again, mostly metals and alloys that are crystalline. So we are going to cover several mechanical properties in this course. We are going to do tensile testing. From tensile testing, we can determine strength and ductility. And we will find out that strength varies inversely with ductility. So if we do something to the material to increase the strength, likely we will have to suffer loss in ductility, and vice versa. If we want to increase ductility, we might have to pay the price in strength. We are also going to do impact testing to measure impact toughness. And we will find out that impact toughness varies inversely with strength. And we are going to do hardness testing. We are going to do a special type of hardness testing called indentation hardness. And we will find out that hardness is proportional to strength. As you will see, that hardness testing is really a very, very simple test. So from this test, at least qualitatively, we can say something about strength. So when we talk about strength, you are going to see role of crystalline defects in strengthening materials. So later in the course, in your lecture course, you will learn that there are crystalline defects called dislocations. And these dislocations move. So if we can create obstacles to this dislocation motion, we can make the material stronger. And we do this by placing these obstacles. These obstacles belong in four categories. They could be zero-dimensional, they could be one-dimensional, they could be two-dimensional, or they could be three-dimensional. So we have, in a limited way, four different types of strengthening mechanisms, because we have four different categories of defects that can act as obstacles to dislocation motion. So here are in a list form, we have solid solution strengthening or hardening. Here solute atoms act as barriers to dislocation motion. So one such example would be carbon in iron. So carbon acts as barriers to dislocation motion in iron. So by dissolving carbon in iron, we do solid solution strengthening. So we use this word strengthening or hardening interchangeably, because as we just mentioned just a couple of slides back, that hardness is proportional to strength. Then there is strain or work hardening. This is caused by cold work or plastic deformation. Again, I'm using a lot of words. They might be look like they are synonymous, but there might be subtle differences in the context in which they are used. So in strain or work hardening, we use existing dislocations that act as barriers to dislocation motion. So these are one-dimensional defects. Then we can use two-dimensional defects like grain boundaries. They can act as barriers to dislocation motion. And finally, the fourth kind is dispersion strengthening or precipitation hardening, where we use phase boundaries to act as barriers to dislocation motion. So this is again a big picture. You are going to probably learn this in about fifth or sixth week of your course. But we are going to be using these ideas in our testing. So when we do material science lab experiments in this course, 306, here are the steps we typically do. So for each lab, there we need to do specimen preparation. This is effectively done by instructor. So I would get the tensor specimen or so, say machined in machine shop, or I would heat treat the specimens. Then I would set up the equipment. The reason I'm mentioning this is I'm going to show you where you are involved if you are doing these experiments in person in 306. Then when you come to the lab, I will have you do some initial specimen measurements. So this is typically done by student. And then I would conduct the experiment depending on the specific experiment. Either it'll be done by the instructor, TA, with or without students. And of course, we acquire the experimental data. And then once the experimental data is acquired, you are going to process this data, you are going to evaluate the result, and you are going to submit the results. So you can see the only things we will not be able to do in this online environment would be doing this hands-on. But you will soon see that I will be having you measure, I'll be having you conduct the experiment in the sense uh, that you will be doing exact measurements and calculations. The only thing would be I would make the hardness indent for you, but give you an image instead of actual specimen to measure. Okay, so what is the new element this semester? I'm going to introduce you to image processing and analysis. Uh, there is a free software called Fiji that you will learn about. Image, by the way, image processing and analysis is used extensively in materials testing and characterization. So if you were to walk over to the next lab uh, in room 2170, which is my research lab, you will find every equipment has got image processing and analysis software and hardware. So what you'll be doing is you'll be using this Fiji as a video caliper. So imagine physically in a lab, you typically say you have a tensor testing specimen or some specimen. I give you a vernier caliper or a micrometer to measure diameter or thickness of this specimen. So now instead of giving you physically the specimen, I'll be instead giving you an image of the specimen. And then with this Fiji as a image measurement tool, you can use it as a video caliper at any scale. So you will be doing basically virtual measurements. And you can use this Fiji in many of your measurements beside material science lab. So it's a very powerful tool. You may want to also ask your friends at other universities about what they are doing in materials lab. See if they use image analysis. And of course, image analysis is routinely used in biology and medicine. So if you go for any of these scans, PET scans, things like that, they all involve image analysis. So I would like you to visit the site, fiji.sc. This is what it will look like. And as you can see, you can download the software. This is free software. You can download it for any operating system. Now, I'm only knowledgeable about Windows system. So all my uh, screen captures and everything would be from the Windows version of this Fiji software. Just as I was installing it, I came across this recommendation that you may want to store it in your user space instead of under program files. So hopefully before we start the next lab 1 demo, I hope that you have installed this Fiji software on your computer. Take care.